Hi student, how are you? Today we are going to continue our discussion on chapter 2, armature windings. So in our previous chapter we have seen the construction parts of the DC machines. At the same time we have seen each and every component in the laboratory. So we'll extend today to specific to armature winding. So when we say armature winding, we say that it is a rotating part of our DC machine, which is composed of the armature slot, the armature winding, shaft, commutators, and bearings. So we'll see how these armature windings are designed and how they are arranged in such type of DC machine is the one which we are going to cover today. So as you know, the armature winding of a DC machine is attached to the rotor, and as the result it is subjected to the alternating magnetic field in the path of its rotation, which is directly results in magnetic losses. So when you see the physical structure of our DC machine, the rotating part is inside the stator of our DC machine. So the stator is the area where the magnetic field is induced. So our armature is going to rotate inside this magnetic field. So it will be exposed for the magnetic losses. So for this reason, the rotor is made of the armature core that made with several low hysteresis silicon steel lamination. It is a special type of core or silicon steel type which help it to reduce the magnetic loss like hysteresis and eddy current losses. So it's a special type which can able to reduce these losses. So these laminated steel sheets are stacked together to form a cylindrical structure of our armature core. So the armature core are provided with slots made of the same material as the core, to which the armature winding made with several turns of copper wire distributed over the entire periphery of the air. As you observe it in laboratory and at the same time in this picture, our armature windings armature core has got a slot. These are the place where our windings are going to be hosted. So a more number of conductors are arranged in a systematic manner. So when we place the conductor in this slot, it is not arbitrary, it has its own arrangement, systematic arrangement, what we call a winding styles, what we are going to see. So this systematic arrangement of this conductor in a slot of armature core, we call it is winding. So based on the way this systematic arrangement of the conductors are made, we will get two basic methods of making these windings: lap winding or lap winding and wave windings. These are the two types of winding which we commonly use in our DC machine. So when we see what a lap winding is, in such a type of winding, a number of parallel paths between conductor A is equal to the number of pole. In such a type of winding in armature, if you see this, the windings are connected in parallel form. So they will be connected to in a brush. So the number of parallel paths inside the conductor, it is equivalent to the number of pole. So paths in the conductor we used to represent with A, small a or capital A, is always A is equal to P in a lap winding. Path is equivalent to number of pole. If we have 4 pole, definitely we'll get 4 paths, it means. But when you come to the wave winding, a number of parallel paths in such type of winding A is always 2. It is always 2. So see this winding, how they are connected. They are connected in series. They are connected in series, and this group of coil are connected in series. We'll only have two passes. We'll only have two passes, no other way. But in case of the lamp, we will have p number of passes, where p is the number of pole of our DC motor. That is their main difference. Their main difference. Again, lamp types have got different type, what we call types of lamp winding: simplex and duplex type. When we say the simplex lamp winding, in a simplex lamp winding, the terminating end of one coil is joined to the commutator segment, and the starting end of the next coil is placed under the same pole, and they're connected with the same commutator segment. If you see this winding, one end of the commutator segment, if it starts from segment 1 and ends with segment 2, and the next segment starts from the next coming commutator, it will be connected to segment 2 and start to the next segment. So that's why we say that the terminating end of one coil is joined to the commutator segment, and the starting end of the next coil is placed under the same pole, we say. So this is under the same pole. This is the first coil, this is the second coil. They are connected to one next to each other. They are laying under the same pole. But when you come to the duplex type of winding, the number of parallel paths between the pole is twice the number of pole. It is twice the number. See, this is the duplex type, and the duplex type, and see how it is connected. And this has got twice, two coils are connected in one, so it has got twice the number of pole. Now our pole is 2, but our current path is 4. Now in this case, our current path is 4. So the duplex lamp winding is mainly used heavy current applications. Heavy, we'll see where they are particularly applied later on also, and it has got twice of the number of pole paths. Let us see a little bit in depth about simplex lamp winding. For a simplex lamp winding, for a simplex lamp winding, the commutator pitch is equivalent to 1, and the coil span is approximately equivalent to pole pitch. So if you see simplex lamp winding, we usually call the distance from this to this end, one coil side to another coil side, we call it the coil span. The coil span, or coil pitch. And the distance from one pole to another pole, north to south, we call it the pole pitch. So in a case of simplex lamp winding, coil span is equivalent to pole pitch, which is equivalent to commutator pitch, and the distance from this center, commutator center of one coil, to the end of the other terminal of the coil, we call coil pitch. In this case, from this center, starting of coil on the segment to first segment, and to the end of the second segment, the second coil side, we call it is coil commutator pitch. So in this simplex lamp winding type, commutator pitch is equivalent to 1, and the coil pitch is equivalent to pole pitch. Just the end of any coil are brought out to adjacent commutator segment, and the result of this method of connection is that all the coils of the armature are in sequence with the last coil connected to the first coil. See, this coil is going to be connected to the next coil, the red one is another coil, and it will form a chain like this to the next segment, coil, so that they form closed circuit winding results. And when we come to the simplex lamp winding, this is a simplex type of lamp winding. simplex, how it is connected. So why it is called wave by itself? It's the shape of the winding formed during the armature. It looks like a wavy type. That's why it is called wave type of winding. It forms a wavy type shape. So in this case, the commutator pitch is equivalent to 2 pole pitch, and the coil span is equivalent to pole pitch. In a simplex it was 1. Now in this case it is 2, and the coil span is equal to pole pitch. And the result is that coil under the consecutive pole pair will be joined together in series, thereby adding together their EMF. See, the first coil side is under the north pole, and the second coil side is under south pole, and the next coming coil side, the first coil side of the coming coil is also under the north pole. They are going to be placed under the same pole. After passing once around the armature, the winding fall in a slot to the left and the right of starting point, and thus connecting up another circuit. That's how this connection waveform is formed. We'll see it in detail later on. Having said this, let us come to the armature winding terminologies. There are common terminologies which we have to have in our mind when we talk about an armature winding. The first one is turn. If you observe this figure or diagram, we call just it is a turn. It consists of 2 conductors connected by end terminus. Here is the starting and here is the end terminus. So we call it is a turn. It has an end term, it has a starting term. This is an end term and this is a starting terms, and this is we call conductors or conductors. These are single conductors. That is turn. And the next is coil. It consists of a number of turns connected in series. See this? They are connected in series, and this side it is called coil side. Coil side. Therefore, one coil has got 2 coil sides. This is called a coil. And when coils are connected together in series or in parallel, according to the connection, if it is connected in series or in parallel, we call it is a winding. This is a winding. These are very basic terms: turn, coil, and winding. And the other important term is pole pitch. The periphery of the armature divided by the number of poles of the generator or the motor, it is called just the pole pitch. That is the distance between 2 adjacent poles. It means it is a distance between 2 adjacent poles. For example, if our generator has got if my generator has got a number of slot of 20, for example, and if it was having 4 pole, so pole pitch, my pole pitch, it is equivalent to S by P, which is equivalent 20 by 4. So the number of pole pitch is 5 slots. What does it mean now? From inside the slot of our machine, inside the slot of my machine, if I have for example, if my slot for example, if I place this coil side in slot number 1, if I place this coil side in slot number 1, and the next side of the slot will come after 4 slots, it means, according to this, it will come after 5 slots. After 5 slots, it is going to be placed. So when we say the pole pitch, we mean that the distance from the north pole to the south pole, or from one coil side to the other coil side, we usually call it pole pitch. Pole pitch. And the other important term is in armature winding is coil span or coil pitch. It is the distance measured in terms of armature slot between two sides of the coil. See this? This is our armature slot, and this is one coil. If you see this side, we can say the first coil side, and the other end of the coil side is this one. So the distance between one coil side to another coil side, we call it a coil span. The coil span from this distance to this distance, or for this slot from this distance to this distance, it is called coil span. If the pole of the span or the coil span is equal to the pole pitch, if it is equal to the pole pitch, the winding we call it a full pitch type. Full pitch type. It means when we place our coil, if I place this coil here, and if it was under North Pole, and when I place this second side, if it is placed under the South Pole, now the coil span is equivalent to the pole pitch. It means if it is happened like this, we call it is full pitch. See this. Now my one coil side is under the North Pole and the other coil side is under the South Pole. So one North Pole, other in the South Pole. Now in this case, pole pitch is equivalent to coil span. Coil span, and the way the coils are placed, it's almost 180-degree electrical line, straight line. It seems straight line, 180-degree electrical. Say type of arrangement, we call it is a full pitch type of arrangement. Full pitch. In a case the coil side lies under opposite pole, hence the induced EMF in them are additive. Means these two EMFs, they are going to add up together and reproduce the EMF. If is a coil span 180-degree, the voltage in the conductor on either side of the coil be exactly the same in magnitude but opposite in direction. It means the voltage under this and produced under this, it is exactly the same in magnitude but opposite in polarity. But if the coil span is not going to be placed under the same pole pitch, for example here, now the one of the coil side is placed here and the other coil side is placed here. Now it's not at a straight line. It means pole pitch is not equivalent to coil span in this case. If that was the case, if the angle is less than 180-degree, if the angle is less than 180-degree, it is called a fractional pitch. A fractional pitch. In this case, there is a phase difference between EMF in the two sides of the coil. In the two sides of the coil. And hence total EMF around the coil, which is a vector sum of the EMF in the two coil sides, and less in case as compared to that of the full pitch. The EMF is going to be reducing. So a rotor winding with a fractional pitch coil, it is called cord type or short windings. Cord type or short winding. See, suppose our machine have 8 pole and it has 122 slots. 122 slots. So our pole pitch, the distance from one pole to the other, is going to be 15.25 slot pitch. 15.25 slot. There is no such 15.25 slots. The number of slots should be integer. But the coil span, when measured in slot, has to be an integer because it represents the number of slots covered in the moving form. The first coil side to the second coil side. So in such a case, the coil are wound with a span just either below or above the pole pitch. It means our pole pitch is coming 50.25. My pole pitch is coming 50.25. See the pole pitch. Now the pitch is coming 50.25. So either we have to make it 50 or we have to make it 60. If we took 50, the smallest round, we call this is a short pitch. This is called short pitch. If we took 60, we call it is a long pitch. We usually name it a long pitch. So if the coil span is equal to pole pitch, which is 180 degree, we call such type of the coil full pitched coil. But if the coil span is less than pole pitch, it is called short pitched coil. And if the coil span is greater than the pole pitch, is going to be long pitched coil. Now in this case, our pole pitch was 15.25, but we are taking less than this 50, which we named it short coil pitch. And if we took it 60, which is greater than the pole pitch, we call it is a long pitch type coil. And these are some tips which we have to have it in our mind when we talk about armature winding. These symbols. C represent number of coil on the armature, N number of turns in each coil, and Z represent armature conductors, and like that. You have to have this in our mind. This relation should be remembered when we talk about the armature windings. And though short pitch coil decrease the induced voltage, it decreases the disturbing harmonics like fifth and seventh harmonics significantly, about 70 to 80% literature indicates. It means where are we going to use this short pitch? What is the advantage and disadvantage? It is telling you that. Therefore, short pitch, it decreases the induced voltage, but it reduces the harmonics, the dangerous harmonics for our machine. That is the advantage of it. And if SB is the total number of our slot and the P is the total number of my pole, then the coil span, like I said previously, it is going to be S by P. And when we place conductors in, now let me show you the advantage of this pole pitch. For example, if I placed, now I said my pole, if my pole pitch is maybe 5, my pole pitch, which is slot divided by pole, if I got 5, for example, if I placed my first coil in slot number 1, slot number 1, then the next coil side is going to be placed in 1 plus 5, which is equivalent to slot number 6. It means when I put my winding in the slot like this, so this is going to be slot number 1. This is slot number 1. And the next side of my coil, it is going to be placed in slot number 6. It means it's in slot number 6. And if I placed my first winding in slot number 2, and the next is going to be 2 plus 5, which is 7. It's going to be placed in slot number 7. This we'll see this in detail when we start discussing on winding design. And the other important point, this is what is already mentioned here, of course, and the other important point is a double layer winding. Double layer winding means that each slot will house or hosts 2 coil sides belonging to 2 different coils. Physically, one coil side is placed in the lower portion of the slot and the other should be placed above it. It is because of this reason that arrangement of the winding is called double layer winding. If you see this graph, 2 coils were hosted in one slot. One is down below and the other is above the slot. That is how they were placed. And there are another terms which we need to consider: back pitch and full pitch. We're going to address this in the next section. Thank you very much for listening to me.